All right. Hello, everybody. Welcome back from the lunch break. So we're kind of going to continue the day optimization day where we left off. So we covered first order optimization methods in the morning, and this afternoon we'll be covering higher order optimization methods. It's my great pleasure to introduce Deeksha Adil, who'll be presenting both for an hour now. We'll have a break, and then there'll be one more 1 hour talk to close out the day. Deeksha is a fellow at ETH Zurich, and she's done a number of foundational works on higher order optimization methods. I think her work has spanned using it for certain sorts of combinatorial and graph optimization problems, as well as advancing optimization theory based on it. It's part of broader work on optimization and algorithm design in general. And I look forward to your introduction to higher order optimization. Thank you.
Thank you, everyone, for coming. And thanks for the introduction. So the goal of these two talks is basically to see what can you do when you know more than just the first derivative of a function. So again, the goal would be similar to optimize a function, but we would try to see that what can you do if you have the additional information of second order derivatives, third order derivatives, and other derivatives. So I'm going to use the board. So if anyone can't see or needs me to write larger, please let me know, and please stop me for any questions. Okay, so let's do a quick recap of what we did in the morning. So the goal was, in the morning we were looking at this problem. So you have to minimize some function x, and the function was convex. So you start with a convex function, and the constraint set is also convex. And what we knew was we had a black box, so we had an oracle that at any point x, so you feed it x, and this gave you f of x and gradient f of x. Okay, and if we have this, then we saw two things, that one was gradient descent and one was accelerated gradient descent. Now for the next two talks, let's just only think about smooth functions. So by smooth, we mean that the gradient was Lipschitz. So for the first order smooth, we basically mean that for all x and y, you had that the gradient is a Lipschitz function. So let me call it L1 Lipschitz because it's first order, and we had this. Good. So for these kind of functions, we saw that gradient descent gives you the rate of convergence. So if you have k iterations, the function error, so the f of xk minus the optimum, this basically decreases as some L1 over k. And when you use the accelerated version, so that we had accelerated gradient descent, you could basically do a little bit better. So we could actually do quadratically better. And we also know that if you only have access to these two quantities, then this is the best we can do for smooth functions. Okay. So these were studied over the 70s and the 80s. So between 1970 and 1985, these two methods were developed. And the question still remained, what can you do if suppose you also knew the Hessian? So for the second order, over the next few years, basically people were looking at what happens when you know the Hessian. And actually in 2006, this was a work by Nesterov. We had the first method that, given, so now the so now the model was the oracle gives you f of x, gradient f of x, and also the Hessian at f of x. So given these, so we had the first method that actually showed convergence when you're given these, and that convergence was much faster, obviously. But so Yes. So in 2006, Nesterov gave a version of second order gradient descent, and which is basically called cubic Newton. Or this is also, let's think of it as second order gradient descent. And this showed that the rate of convergence oh yeah, so I missed one thing. So again, we're looking at before I state the rates, we're looking at functions that are second order smooth. So we had rates here for functions that were first order smooth, so the gradient was Lipschitz. But now we want to look at functions which have the Hessian to be a Lipschitz function. So you're looking at functions that are second order smooth. And this basically means that for any x and y, you have this is less than some L2. And this norm is the operator norm. And here we'll just deal with Euclidean norms for today. Okay, so for these kind of functions, you can actually do something that cubic Newton gives you a rate of convergence that's actually similar to accelerated gradient descent. And soon after, in 2008, this was Nesterov and Polyak. Okay, and in 2008, there was another improvement to this, and this was again by Nesterov. And he gave an algorithm which was analogous to the accelerated gradient descent, and he called it accelerated cubic Newton, and that basically gave you a rate which was to the k cubed. Okay, so until 2008, we had some things about second order methods for smooth functions. The extensions to this, to let's say, so we can now look at what we mean by pth order oracles. So before I explain what we actually mean by these kind of smoothness and what can you get with these kind of smoothness, let's first just define what we mean by pth order oracles. Okay, good. Okay, so now as a similar extension, you start with x and you want to know f of x, gradient f of x, and all higher order derivatives of f of x. And given these, and now again, we would look at functions. So we looked at L2 smooth, where the Hessian was smooth. We saw L1 smooth, where the gradient was smooth. So a natural extension is we'll look at functions which are LP smooth. So that means that the pth order derivative is Lipschitz. So you want this condition to hold. Okay. And what we mean by this norm, so this norm basically means that you want to find the max so this is like a pth degree tensor. So you want to find the maximum of this value such that right. So this is basically an extension of let's say the operator norm to higher order tensors, and this is just the directional derivative of this along these directions. So this is like an analog of the operator norm to these higher order derivatives. And what I mean by this quantity, this is the directional derivative of directional derivative. Yeah. Okay. So today we'll look at these kind of functions basically. And yeah, so we have these p derivatives. It's LP smooth. So the pth derivative is Lipschitz. And this is the norm we are working under. Okay. So you may ask that how are these Lipschitzness related to or anything the first order, but these are like totally unrelated. Like the gradient can be Lipschitz, but this may not be true, or this may be Lipschitz and no other derivative may be smooth. But like a simple example is you can just take the function f of x is x to the p, for example, and the p minus 1's derivative is Lipschitz, but none of the others are Lipschitz. Yeah?
Simple question. So you're taking the max here over h, whereas in general one could take the max over h1, h2, h3.
Yeah.
HP. Is it the same? Was it in the case of p equals 2, it's achieved for a single h?
Yeah, I think it's the same even for higher orders. Yeah.
Is the Lipschitzness of the pth order derivative equivalent to a bound on the maxi of the norm of the p plus 1?
Yes, it's the same.
Isn't that more convenient to work with?
It's more convenient?
Yeah, isn't it more convenient to work with the p plus 1?
Yeah, you can work with that, but I mean, the way we use these Lipschitzness is I'll get to how we're using these, and in that case, it's easier to work with this definition. Okay. Okay, so yeah, before I tell you the rates, let me give you an example of a function that is, yeah?
Sorry, just checking. In those rates, should the squared be cubes in the distance to opt? For second order smooth, should it be like x1 minus x star cubed?
Yeah.
Thanks.
Okay.
Thank you.
Okay, good. So right, so one example of a function which is actually, smooth for all orders of p, and that function is going to give an example of that function, and that function has actually helped in many combinatorial optimization problems. Like you can use that for modeling L infinity regression, you can use it for matrix scaling, you can use it for operator scaling, and it's basically a smoothing of infinity regression, which we call the softmax function. And let me define it first. So this is one. So here's an example. So let's see. It's called softmax with parameter mu. And this is defined as so this function is so there's in this paper, let me check which one. Oh, sorry. Thank you. Yeah. And there's also one over here. Yeah. Okay. Thank you. Yeah. So in this, you can actually show that for this, so there's this theorem which proves that this is higher order smooth for all p. So basically it is some p plus 1 by pth order smooth. And yeah, some computation can show you if mu is something like epsilon by log n, then it approximates infinity regression to an epsilon additive error. And a lot of these matrix scaling problems, especially this, few of these works actually model their things as softmax objective and they try to optimize over that. Okay. Good. So we do have functions that are good for all P, and for these, if you use some higher order oracle, then maybe you can do a lot better instead of just using first order oracles. Okay. So in the sense of algorithms for these higher order smooth problems, so the first algorithms are actually in 2009 and 2019. There were two different works by, one was by Bayes and one was by Nesterov. And they gave an analog for gradient descent to these orders and an analog for accelerated gradient descent. So for gradient descent, you basically, let's say Pth gradient descent, you basically get something that's going to ignore all the other terms and just focus on the epsilon convergence for now. So this goes as 1 over P, and accelerated gradient descent actually gives you 1 over. So you can go from 1 over epsilon to the 1 by P, and here you have epsilon to the 1 by P plus 1. And regarding the optimality of this, we'll look at that in the next lecture where, so the short answer is this is not optimal for P. It's only, so the extensions of AGD are only optimal for the first order, but for higher orders it's not, and we'll look at the optimal algorithms in the next part. Yeah?
So I assume for accelerated gradient descent to work here, you also need some kind of lower bound.
Right, so the lower bound is just from convexity actually. Even if you recall in first order AGD, you only used smoothness, which is Lipschitzness of the gradient, and you used convexity, and we didn't really use anything else. So here also we just have this kind of Lipschitzness, and we have convexity of F.
So you just need like first order convexity.
Yeah, first order convexity, that's sufficient. Okay, so in this talk we'll focus on, I'll try to give a proof of this pth order gradient descent. Okay, so before we look at that, let's see what does this pth order smoothness actually give us. So in the first order, I erased that. But for the first order smoothness, we were able to give an upper bound for the function. So basically from first order smoothness, we could say that if a function was first order smooth, so you could write this kind of upper bound for the function. And gradient descent, one interpretation was that you just minimize this at every point. So if you are at iteration xt, you just minimize this, and you minimize this to get the new point, and then your new iterate is just the minimization of this upper bound. So we want to use the same idea for higher order things, but so from pth order, so let's just look at second order as a simple example. So when t equals 2, we basically have, let's go here. So yeah, for p equals 2, now I want to do something with this and see what kind of upper bound you can get. So a simple integration exercise will give us two things. So the first one set of integration will give you so if we just do some integration, some calculus here, the first do it once, we get this kind of bound, which is so what is this saying? That you have this gradient at x, then you have some Taylor expansion of this gradient. You have around this point y, and this difference is bounded in some way. And if you do another round of integration, what we would get is if you do one more, then you basically get this. So you can, what we see is you're basically, because of this, you can bound the function at x with a cubic polynomial essentially. So this second order smoothness gives you a cubic polynomial as an upper bound, and the same thing translates to pth order smoothness. So for p from LP Lipschitzness, you can basically get for any x and y, you can So you can bound this by the Taylor expansion around a point plus some distance term, as Alina alluded to in the morning, that you have this Taylor expansion and a distance term. Okay. So the first algorithm that we would want to naturally look at is, okay, so let's start with some x0. So let's say this is some potential algorithm. Start with x0, and you want xk plus 1 to just be argmin y of basically this function. So if I call this function some, let me call it omega of y at, so okay, so let's say at the Taylor expansion centered at xk and some function of y. So the algorithm is you just want to minimize this upper bound, and we want to see how does this converge. Okay. So you may ask that why is this doing this any easier, minimizing this upper bound? And the short answer is that for p greater than 2, it's still an open problem to find efficient ways to minimize this oracle. But under certain models, which, like there's this work by Aaron, Arun, and group, which talks about a ball oracle, which is essentially some high order p oracle that solves this. And for Hessian stable functions or like some good functions, you can do this very efficiently. So, okay, so it still remains open if you can solve this. But we know at least one fact. So Nesterov in 2019, he proved that if you reduce this to actually p minus 1 factorial instead of p, then this upper bound, this is a convex function. And once this is convex, at least you know there exists a solution, and how to find it is, at least there exists a unique solution. Okay, are there any questions? Yeah.
So if there is no unique solution, which one do you pick?
Yeah, so to make it well defined, we actually use this upper bound instead of the one with p factorial. I think it's just convex. Oh, if it's not strongly convex, then you can just pick any of the minimizers. But at least they'll have the same function value. So that's okay. Yeah.
That seems very sensitive to the constant. At least in the case of the gradient descent, I think this was very insensitive to the constant.
So actually, the thing is, you can use anything larger than this. And yeah, you can use anything larger than that. It doesn't matter. But yeah, this is the minimum you need for it to be convex. And okay, good. So now okay, yeah. So there's a proof of why this is convex in Nesterov's 2019 paper called Implementable Tensor Methods. And so if you want to look it up, you can look at it. But he basically just uses the second derivative of this and shows that it's the second derivative of this f of x is p is b. So the other one is kind of around it. Okay. So now let's actually look at this gradient descent algorithm.
So it's known that it's not convex for some functions.
Oh, that's a good question. Yeah, I'm not sure about that. If it's known that it's not convex for the other, but we know that for this it's convex.
Something basic about it. Do we not want P to be odd?
P to be odd? I don't think that matters actually.
Seems
But I think you basically, when we think of large P, we usually think of something like log n also.
we'll know that.
Yeah, I'm not sure if we know if a function for which it's not convex. Do you have anything to add?
No, I'll repeat what I said to you. Just like gradient descent, also, if you take too big a step, which is the same as too small a regularizer, eventually it'll diverge rather than converge. So the meaning the regularizer to be at least something.
Sure,
That seems like a common thread. Now, the fact that it's not convex in the starting regime needs to be larger. That is an interesting thing, though I don't know the answer to your wonderful question about necessity.
Any function if the constant is large enough as well.
Yeah. So for any smooth, pth order smooth and convex function. Right. Okay. Now let's.
Sorry, I was only there are maybe interesting things about even and oddness when you talk about implementability. But when it comes to just the method working, yeah, I agree with what you're saying.
Yeah. Okay. So let me make this here. So yeah. So let me define. Let me define this to just be the first the. I'm going to just use a small. Okay, I'm just going to use this to denote the Taylor expansion. Taylor expansion around X. So this is the pth order Taylor expansion around X plus okay. And the algorithm is so let's just think of unconstrained problems and not worry about the constraints at this point. And so this is the algorithm, and let's see how to analyze this. Okay. Good. So the analysis is actually surprisingly not very difficult, and it essentially needs two tools. And the first one is this. Okay. So we want to prove this is again semester of 2019, and all k greater than 0, you want to prove okay, so this is what we want to prove. So let's ignore all the constants. Let's just think of this as some radius. So let's replace it with some. So it's inside some big box. And we'll just look at this. So you just have this k to the p essentially. in the bottom. So if you want to go down to epsilon, it becomes something like 1 by epsilon to the 1 by p. Okay, so we want to prove this, and in order to do so, the first key thing we will show is that, which is the first thing we want to show is we want to characterize what does this thing at k plus 1 do. So we have this, that f of x k plus 1 is basically less than So if you look at this, at any point, this f of x k plus 1 is less than the minimizer of the function at some, oh wait, sorry. Okay, yeah, good. So at k plus 1, it's basically less than the minimizer of the function plus this is like some small regularization term. So if you're actually close to the optimum, even in distance, this would be very small. So yeah, you're within like some bound to the optimizer. And a very quick proof of this is just, yeah, right. So the solutions that you're actually getting by minimizing this upper bound is in some way not too far from these. And to see this, let's, yeah. Oh, I also forgot to mention one fact that from this, we also know that f of x k plus 1 is less than basically, so you know that f of x k plus 1 is less than this. And this is again proven in this paper. Okay, good. So given this, and this is actually easy to see. So we start with using that fact. So you start with, we know that f of x k plus 1 is less than. And if we recall, this is just the Taylor expansion with some regularization parameter. And this we know is minimum over x of this function. So we know this is true just by definitions. And if we expand this, so this is just again the minimum over x of this Taylor expansion. Yeah. So this is just expanding this, so we know this. And now we can use a bound from pth order smoothness, which is, okay, so that's gone. So the bound on, you could bound any function by the Taylor expansion plus the regularization. So you could use that, and this would give us, so it follows from smoothness, and you just get plus some, some constants. Let's not bother about them, and you get this. So the only thing we use here is the definition of what we're minimizing and pth order smoothness. And now we'll use this to actually prove our, So, okay, so we want to prove this. The easiest way is we'll just use induction. So for k equals 1, so let's use induction. For k equals 1, we start with this. So this is always true, and we know that x1 is at most okay. So this is just using our lemma A, and then this you can just split the min within these things, and you just get f of x star plus.
Sorry. I feel like I still don't understand the proof of lemma A, actually. So how did you do the last transition again? It seems that you replaced this T with the F and...
Oh, so I replaced this t with f plus some constant times this term.
Uh-huh. Right. But then in the statement of the lemma, the constant is LP over P factorial.
Yeah, so there's one more constant that adds up to this.
Ah, and this is P minus 1
Yeah.
factorial.
Maybe I messed up the constants, but
All right, yeah.
basically you get some constant here from the definition of this, and then you get another constant from here, and that adds up to this.
I'm still a little confused because this... So somehow, one thing I can't reconcile is the following. T is an upper bound on F. So in this lemma, the right-hand side is could, it seems, generally be significantly smaller than the minimum of the T.
But it's also, you also have this, so it's an upper bound on, okay, good, that's a good question. And 1 second. Yeah.
I think T is an approximation of F up to something involving the distance between the center and X.
Right, but it's still an upper bound.
And a lower bound.
And
It's
a-
like both.
It's like an
It's not-
absolute
it's-
value.
The lower bound is only convexity for 1. When you go past 1, you can bound how far it is,
Yeah.
but it's not necessarily above or below.
Yeah.
Okay,
Basically.
well, that explains.
Oh, I guess 2 it's still above because of convexity. 3 is where it gets funny. I
Yeah.
guess. Okay.
Good point. Just to make sure. So in reality, this. Okay, so I'll just repeat it to make sure I understand. Is it right that in reality, this T plus a constant times the movement cost with a P power, P plus 1th power, this actually sandwiches F on both sides?
So
It's lower end and upper bound.
the movement part may not really be a lower bound for this.
So otherwise, I don't quite see how this follows without a lower bound, right? It's just that the right-hand side, it's a minimum of f of y over all y. And if t only provides an upper bound, I'm just not quite succeeding in imagining how we get it, right?
Okay. Okay, so
So we work with t, but maybe we can take it offline also.
yeah, we can take it offline. I can actually show you. It comes like you have this f of y minus this Taylor expansion. Absolute value is upper bounded by this quantity.
Yeah, I'm just confused.
No,
So-
that's an upper and a lower bound. Right?
Yeah, there's an upper and a lower bound. Yeah, there's an upper.
It's like the absolute value of the difference is bounded by the
Absolute value of
By the
f of
movement cost. And then,
Yeah.
then I'm with you. All right.
You can
Yeah.
just Taylor expand, but the theorem of the last term, where you truncate and then just like plug in.
Oh, I see.
Yeah.
It's basically Taylor expansion. Okay. All right.
Okay. Okay, good. So, yeah. So we were showing this. So if you want to use induction, so for k equals 1, we just use lemma A and split the minimizer, and yeah. So this can just be this can just be an upper bound on the set, on the diameter of the constraint set. Okay. So this is what we want for k equals 1. So now let's do a similar thing for So what we really want to show next is, if you want to show it for k, you want to show that the distance to the optimum at iteration k plus 1, how much is it lower than the distance to the optimum at iteration k? And so if you show for k greater than 1, let's again start with this. So you have so you start with this again. Okay, so the minimization is overall space. So this is less than, you're doing the minimization over, let's say, some, and I'm changing y to be the minimization over all space versus now I'm just optimizing over this line joining xk and x star. And this gives us LP okay. So we basically can reduce this to a minimization along between xk and the optimum. And now this is a problem in alpha scalar, and minimize it at least. Let's just take the derivative and set it to 0. And let's hope that that lies between 0 and 1, and then we're good. So just looking at this function, taking derivative, setting it to 0, let's say that gives you alpha star. Oh, actually, let me do one more step before that. So I'm going to use convexity of f first. So this is the same as okay, yeah. Now this is much easier to minimize. I just use convexity to split this. And now minimizing this over alpha, you just get alpha star that's equal to, let's say, okay. The optimum alpha for this just gives you something like this. And this we know is at least greater than 0. And if we want to show whether this is less than 1, I claim that this is also less than 1. So you want to see that. Okay, so I'm going to claim that this is less than 1. And okay, maybe I'll skip that for now in the interest of time so I can, yeah? Yeah, R is, let's say we have a convex set, R is just some radius for the convex set.
So it's not unconstrained.
Okay, good. Or let me say that R is rather, it's an upper bound on x1 minus x minus x star for all the iterates x. So let's do that. Okay, good. So we want alpha star less than 1, and I claim that this is less than 1. And I'm going to skip that for now. Okay, so given this, we resubstitute this back, and let's see what happens. What is this? Yep.
Just checking, is that less than 1 for all iterates or just like after the first iterate?
Oh, it is after the first iterate.
Okay. The first iterate though.
Yeah, the first iterate is, yeah.
Okay, so all subsequent ones.
Yeah. So so if I resubstitute back alpha, put alpha star back. So what we would get is of x k plus 1 xk minus I'm skipping a bunch of calculations here, but but just by substituting this back and doing some algebra, you can get that this function at k plus 1 has actually decreased in some way. And if I do something more, you can actually say that the distance, so if I just subtract an x star, can get this. X star. Y minus x star. So in some way it's decreasing, but recall that this alpha star actually depends on this difference. So if you replug that, and let me just call this the difference at k plus 1, and this is the difference at k. So what we would really get is minus some constant this is just putting these things back in and you get this. And the way to go from this, so now we want to use this to show something about how many iterates you can get. And a sketch of how to do this is, let me just ignore this constant here because let's ignore all the P, L, P, R dependencies and only focus on how you can get the dependence on K. And if you want to use this, the easy way is I'm going to look at this difference. So I'm going to look at this difference, and so this can be so just shifting things around, and can further okay, I can further write this as okay. So just doing some algebra, you can add and subtract some terms, and this is exactly equal to this. And now we want to use this bound that we know from here at that point. So this just implies that
So like in front of the p plus 1 over p powers term, do you have extra constants that you're hiding?
yeah.
Okay.
Yeah, I just left the constant.
Otherwise, you just make negative progress.
Yeah. No. There is some constants there.
Yeah.
Okay. Yeah, this just implies that this is, oh, sorry, it's 2 delta k. We just use this bound over there, and some more simplification will actually give us that this is greater than. And so it will give us some ratio like this, and I claim that this is greater than 1. I mean, we claim that this the distance keeps decreasing, so you can just say this is greater than 1 by p. So once you have that this difference is greater than 1 by p, you can induct over this difference, and in the end, okay, so this part is good, and so we're almost done. Let's take this out.
Like,
Yeah.
does this mean that like progress slows down as you approach your minimizer? Like initially, like when you have like a huge function value error, it seems like you're making a ton of progress per step.
Yeah.
But then like when you're like near, you make just like very.
I mean, this exactly what it's giving you is this. Maybe this is easier to see.
I just like don't see it.
So what is this might be, so we had this. Yeah. So I mean, this just gives us something like, oh, sorry. So this is just something like k times k by say k minus 1 by p plus.
I mean, the reason that, okay, basically why I'm asking is that somehow it feels like whenever you're like, your error is small, somehow I was hoping that your approximation would be good enough that you actually still make good amount of progress. Like your, like it doesn't get much slower than in the beginning. Right? Like basically I'm just looking at like how delta k evolves according to your bound, right?
Okay. So how delta k evolves?
Right? Like you're saying like delta k plus 1 equals delta k minus delta something times delta k to 3 plus 1 over, right?
Yeah.
So like when delta k is like humongous, that's kind of great for you.
Yeah.
When it's like when you're super close to your minimizer, that's like that gives you like very small progress. Like it's a very
That's also true for gradient descent too, right? Because you're close.
yeah, fair enough.
Yeah. So it's an extension of gradient descent, so it kind of does this. Okay, good. So once you have this just gives us compound delta 1 by. We can just use something for the initial error, and you can basically see that delta k plus 1 is something like, you know, some constants, problem dependent constants, and you just get this k to the p. Okay, great. So, so you basically can see that if you just use these higher derivatives, you were able to get some improvement over the first order cases. And I'm going to stop here for this one, and we can come back and see how to accelerate these algorithms in the next one. But I'm happy to take questions if there are.
Thank you. Questions?
It's a bit unrelated, but if you only have a zero-order oracle, can you still do gradient descent under some reasonable assumptions?
Or if you only have something that gives you f of x,
Yes.
I mean, then what would you mean by gradient descent if
I
you
mean,
don't?
but you can still approximate gradient, right?
Also, you have some. So you're trying to say, is it that you have some approximation to the gradient and?
No, but I mean, you can just, by definition, you can approximate gradient if you take delta t to be not just small enough, right?
Yeah, I don't think I get your question.
Like a random vector.
So yes, there is work on zeroth order optimization. There's
Oh, I
actually
see.
there's like different work on actually like what if you have second order Lipschitzness but only a gradient oracle, or you have
I
like
see.
gradient Lipschitzness and only a zeroth order oracle. Also, and what if you have all sorts of variants of this are studied.
Oh, yeah.
I think there are a lot of
I guess
interesting
that's
stories to tell depending on which setting you have. But
Yeah.
Is there some smart way of approximating this gradient? The only one I know is take x plus perturb the tiny bit into 1 and evaluate. Are there better ways?
Just like you do your test, like a perturb x with some random Gaussian, and basically evaluate the function there that gives you a gradient estimator, sort of slightly perturbed function.
Great.
Oh, yeah. That's not
I'm happy to discuss this after.
Well, that's good for offline.
Any other questions? Do you want to say a little bit about what will happen after the break? Before we
Oh,
take a
yeah.
break?
So
Listen a
after
little
the
more?
break, so as I said, the first, so this was an extension of gradient descent. The extension of accelerated gradient descent does not give us the optimal rate. So we'll see how that looks like, at least the algorithm, and we'll see what the algorithm is that gives you the optimal rate, and we'll look at that algorithm. But the optimal algorithm has actually proven very useful in giving some of the optimal higher order algorithms for, let's say, regression problems. Even you can directly get CKMST max flow from it, and there have been many applications. But those applications we might have to take offline because but I'll at least give a sense of what the algorithm's like. CKMST is this 2010 work by Cristiano, Kellner, Madri, Spielman, and Teng that accelerates max flow using so yeah, got yeah.
Thank you again. All right, so we'll have a break now until 3:30.